In this video, we are going to learn about the Tusi couple and see how circular motion can produce straight line motion. First, let us look at the final visualization. In this animation, you can see a small circle rolling inside a larger circle. As the circles move, observe the tracing point carefully. Even though the motion is circular, the tracing point moves only along a straight vertical line. This beautiful mechanism is called the Tusi couple. Now, let us see how to create this animation step by step using Point2Space. First, click the Create icon and select an area on the canvas. From the toolbar, select Graphs, and then choose a 2D geometry graph. Now the graph is created. Next, create a point at the origin. Using this point, create a large circle with radius 4. This will represent the outer circle of the Tusi couple. Next, create a scalar variable from the definition section. Let us define a variable called a and set its value to 2. This variable will control the radius value used in the construction. Next, create two function variables. The first function defines the x-coordinate of the center point. The second function defines the y-coordinate. These functions create circular motion for the center point. Next, create a variable animator and name it as t. Set the animation range from 30 degrees to 360 degrees. Using the Move feature, we can align all the expressions neatly on the canvas. Now let us create a point using these function variables. This point represents the center of the small circle. Next, create a small circle using this moving point as its center. Now we can connect the origin point and the center point using a line segment. Next, let us create an angle marker. To create an angle, we need two lines. If you don't want to display the point, simply click the defer option to hide it. Using the multi-select tool, select both lines. Then click Operations and choose Angle. Now the angle marker is created, we can also edit this angle and add an arrowhead for better visualization. Next, add a label for this angle marker. Now let us mark the point labels. Now let us define the coordinates of the tracing point using functional variables. The x-coordinate is defined as Notice that the horizontal components cancel each other, so the x-coordinate always becomes 0. Next, define the y-coordinate as here. The vertical components add together, so the tracing point moves only up and down. Now create a point using these tracing equations. The trace point is created using functional variables. When we play the animation, you can clearly see that the point traces a straight vertical line. Now, create a line from the center of the small circle to the trace point. This line will help us create the angle marker for the trace point. Next, add a label for this angle. Now, let us create a triangle to visualize the motion components. This triangle helps us understand the horizontal and vertical components. Next, create a triangle using these 3 points. Using the polygon tool, we can create the component triangle. Now let us mark the x-coordinate and y-coordinate components using distance markers and text labels. The horizontal component is represented by and the vertical component is represented by Now let us create another triangle for the tracing point. These triangles help visualize how the components cancel and combine. The shaded triangle makes the motion components easier to understand. Now let us add side markers to the tracing point triangle. Let me add a focus effect for the horizontal components. Next, we can add a focus effect to the vertical components. But the vertical components add together. As a result, 2 sine theta Now we can hide some of the construction components to clearly visualize the final circular motion. Now let us animate the variable values using the animator. Next, we play the animation. You can clearly see that the point traces a straight vertical line. Now, let us hide the graph and replay this animation to observe the circular motion more clearly. This means the large circle has twice the radius of the small circle. The outer circle radius is represented by r equals 2a. This demonstrates how circular motion can produce straight line motion in the Tusi couple.